screen. Here we go. Do you see the screen?
Yes, perfect. Thank you.
Excellent. So thank you, Gilbert and Pierre, for contacting me and inviting me to this lecture. As Gilbert has said, Anya Apolinarska will lecture in September. So certain things that I will show are part of their work. She will eventually show them again and go in much deeper detail, having more time. I'll try to give sort of an overview on the work. First, let me start by saying that Matthias and myself are not particularly known or exclusively known for timber architecture. Indeed, we are known for robotic fabrication, digital fabrication, robotic construction, and we got in touch with timber about 10 years ago because of its digital workability, processability. And then got more and more interested into it, started to scale up processes. I will show this sort of evolution in the lecture today. And at the same time, this in the last 10 years, the understanding for what timber really is also grew. And as Pablo has nicely laid out in the previous lecture, making very clear that timber is the material of the future. We like to say that it's probably will be the concrete of 21st century. It would do to the 21st century what concrete was able to do with 20th century. But before going to timber, I would like to introduce, just to allow for an understanding of what drives our interest and why timber is particularly interesting beyond its advantages in terms of sustainability and so on. I would like to talk about digital materiality. And timber is, for us, a digital material, sort of. When we started 15 years ago to work with an industrial robot, this is a staged image, of course. It's an artist image that very nicely show what all our work since the very beginning is about. This understanding, or our own understanding of this, has of course evolved throughout the years, but this image that I think is 2008 still captures it very nicely. So architecture is about us humans and technology. The technology here is represented by this orange industrial champion or monster, 6-axis industrial robot. This is a commodity in industry. It's a mass-produced tool. It has been invented in the 50s, beginning of the 50s, introduced very quickly already in the 50s in car manufacturing. General Motors and Ford started to set up lines substituting human that were doing welding, for example, with robots. This was a job robots could do very well. Of course, back then they were not that sophisticated, but actually this machine has remained the same. So it's nothing else that the possibility to numerically reach a position in space in a very complex way, and then perform an action. And this is, there is the kinematic of it that is anthropomorphic. This is also why this is the only machine that has this strange name of robot that was invented or introduced by fiction, literature, movies, other machines, even if they are much more complex, sophisticated, and intelligent, are not called robot, have specific names. The robot is absolutely generic. This is what makes it so attractive and also similar to us humans. It has not been designed or optimized for a specific task, but is open for interpretation. And this is what makes it an interesting architectural tool, because it doesn't come with a process attached to it, but with a possibility, with a potential. And then to imagine and to implement this process becomes part of the design process. The second thing that you see here sitting on the arm, what is clearly extremely dangerous and forbidden, you'll never see this in industry, is a human. This was our first collaborator, Mike. Back then he was extremely young, and he operated the robot with us. And what the image shows is holding the teaching pendant in his hands that control the robot. So there is a circularity. The robot depends on us as much as we depend on the robot. And this is an important finding or thing we realized at a specific point, and that grew also, and that now informs all our thinking. It's about the relationship between humans and technology, and humans and machine, or architects and technology. Being still, and we experienced this, having studied in the 90s, so at the very beginning of what was then called, digital parametric architecture, mainly being concerned with complex form or shapes, blobs, for example, that could not be often then produced. It ended up being competition, mass competitions, plans, renderings, so synthetic images. We felt that this relationship that, as I said, is still very, biased by our understanding that was formed in the industrial era. So I say from the mid of 18th century until the almost end of 20th century. When our society got used that technology, say machines, were big tools that substituted at a certain point, starting with textile industry, but then, going through everything, started to substitute the tools of the craftsman. These tools become bigger, more productive, more efficient, and Fordism, Taylorism, leveraged on these tools, became that expensive that they could not be owned by a craftsman, so a person producing things anymore, but they had to be owned and controlled by capital. And the process of producing things has been divided in an infinite amount of small steps. This is what we got used in 20th century to call the alienation of work or of production. So this is when I am not under control anymore, and I don't understand what the final goal or output of something is. I'm just adding a little action to a big complex chain of steps. And this is where, and ultimately, and then this is the social question, these machines were, that their ultimate goal and the goal of the people that own and develop the machine was get rid of humans in the production of things, because humans are a source of trouble, of errors, of costs. And this extremely negative competitive relationship, that started with philologists burning down factories in end of 18th century, is still with us. Latently, if you think of machines, there is this technophobia around. For example, every time we show a robot, first question, it's not so frequent anymore, to be honest, but the first question is, what about the humans? Happening with the humans? Will they be just substituted by machines? And this is not the point. And I will demonstrate why we have an understanding of this relationship that is cooperative in the true sense of the world. In order to do this, now we'll do a thing that is a bit unorthodox. I will talk about a brick wall. In a timber lecture, this is it's like talking about timber in a symposia of concrete industry. You get thrown out, but I'm on Zoom, so it's not a problem. But I would like to show this because bricks allows to explain extremely clearly what digital materiality is for us, and then to transfer this knowledge to timber. That, of course, augments its potential. But it will be a 5 very didactic minutes. Sorry for that. We have a brick wall, as we know it. And the question is, in architecture, in design, how do we represent it? So what's the notation we have or can use to describe it? First of all, a very simple one is to just draw it. This is what you see here. You can draw it by hand, draw it with pencil, print it, whatever, but you have a visual depiction of it. This is very powerful as a notation because you immediately understand what it is. But when it comes to construction, it's also very weak because it's very complex and very unclear and very inefficient. Now, the history of construction or of culture and construction has generated a concept like the bond, which is nothing else than a set of rules that are shared in a cultural area where that encapsulate everything, encapsulate the sequence. So everybody understands how a stretcher works, and every mason, can just do it. And the only thing you need, or humans need, to do a stretcher bond is a few simple parameters that boil down to the element, the size of the element, the type of the element, the length and the height of the wall. That's it. There is this advantage here that with a minimal description, a minimal amount of data, you're able to instruct something very complex in a very lean way. Now the question for us, if it comes to machines, is what is the equivalent in digital fabrication? So if we have to talk to machines instead of humans on a building site, and the machine clearly, even if now we have artificial intelligence and machine learning, the machine doesn't understand what a stretcher bond is. How should she? So machine understand data, numbers. And the nice thing here, this is why I use this example to explain the problem and its potential, is that there is an algorithm that actually is the basic algorithm of everything, the basic control structure that is a loop. A loop is in programming just the instruction to repeat something, an action or a computation for a certain amount of times until a certain condition is satisfied, for example. Now, a brick wall is nothing else, is the direct correspondent of a nested loop. A nested loop is as simple as a loop. It's just two loops nested one into the other. And this is what you see here. You know, 4, then again 4. One takes care of the rows, you know, because the action in the inner part of the inner loop is just saying put the brick next to the last one. You know, this is the brick, the stretcher bond logic. And then you repeat it until the length is satisfied. You reach the wall, for example, or a limit. Once this is done, in the outer loop, you know, the position of the whole thing is raised by 1 brick height, shifted by half brick height, and repeated. You know, so another row, and when you reach the ceiling, you're done. You know, the algorithm stops. So this is a different notation to describe the exact same things to a machine. You know. Now you could say, so what? You know, the trick is here. If now we look at this code and recognize that we don't have to use it just like this, but we can add, for example, these 2 pink lines at the bottom. Everything else is the same. 2 pink lines have been added, and there is some computation happening there that is, as the names of the variables suggest, it's about a rotation. So the brick is there, not just placed, but rotated on its central axis, center point. And these 2 lines, you know, are an act of design. This is the human on the left. In this case, it's a student. The student looks at the material, touches, you know, tests with its hands the possibilities in space to do something, and then he writes these 2 lines. So actually he's designing, and this algorithm, so this stretcher bond, is not a generic stretcher bond now anymore, but is this outputting this, you know. So it's a very unreadable list of numbers, but you can trust me, these numbers are nothing else than XY positions and a rotation. The XY position is easy. The rotation is not, because each single of this brick of the wall we have seen before now has an individual rotation. And this is the thing you cannot communicate anymore to a human, but can communicate it to the machine. And you can communicate it better because the machine doesn't understand what a stretcher bond is, but the machine understands very easily, because it's the only thing a machine understands, a number. And the number correlates to the position of a motor, for example, to an axis, and at the end to a position in space. So what we have here, if we, you know, go back to the beginning, we have the possibility to directly connect the act of design by a human with a machinic execution. And this is extremely powerful for a few reasons. First, because it goes beyond automation. You know, it's not about automating something we already do. It's about reaching out in a domain to which we don't have an access usually. And the second thing is that there is no competition between the human and the machine here. You know, because the human needs the machine. Otherwise, there is no reason to, you know, design 5,000 bricks with an individual rotation without the machine. And the machine needs the human, because the machine is not designing anything. You know, the machine is just executing things. Yeah. And this very simple exercise that in this was the very first experiment with this machine when we installed it as a proof of concept. And also the bricks are more or less the consequence of pragmatism, because we needed elements and we looked out for interesting elements we could get for free or very cheap, and then suddenly we had this in front of us, something that is, and here at this moment we coined this term digital materiality, just instinctively. And throughout the year, then we started to understand what it really is, because here something happens that is both, related to the physicality, so three-dimensional space. It's all about light, and light is just reflection of waves on a surface, and it's just about the relationship between the position of the light source and us, so the observer. Light changes color or makes color visible or at all. And at the same time, beyond this very familiar material, something happens that we have never seen so far. We were used to see these things from the two-dimensional domain of graphics, for example. Computer graphics in the 90s were already popular, but it was always two-dimensional. Here it's weaved in the material. So it's these two apparently very different domains that in the 90s, when we were architecturally socialized, were enemies: the digital and the physical, the digital and the material, the digital and the analog, no communication. Here they come together and they merge. And with this knowledge, we then, and this just a few images, we did one or two projects where we scaled this up, and then really understood what happens at that certain scale. What is this? What is the potential of being able to control material at a very high resolution, And we understood that we don't need, a techno material. We need very traditional materials, and just need to inform them differently, and then they become a new material. So our claim is that while in the 20th century has been formed on truly new material, physically new material, steel, glass, concrete, the 21st century also has new materials, but it's not the physical base of them that makes them new. It's the integration of digital processing and design that turns them into new materials. Okay, now let's move to timber finally. This is the projects that I haven't shown for probably about 10 years, but thinking this morning about how to tell this story, I searched for them. These were first studio works, 2008. This was 2 years after starting at ETH with this machine, where at a certain point we wanted to explore what happens if this bulk material, the brick, so standardized, mass-produced material, can not only be placed at a certain position in space, but can also be processed. And timber is nice because it's an industrial mass-produced material that comes in many shapes and CLTs, layerings, and so on. But actually, if you have a slat, for example, you can cut it to length with a very simple operation. You can cut it to length and you can choose the angle of this cut without adding any complexity to the fabrication process. And here you see first studies. These are model studies with students where we try to find layering logics that would allow for parametric, first of all, description of it, and then design, the manipulation of these things. This happens physically, this happens then digitally, You know, you have to find out, okay, what is the degree of freedom? When do things collide? How is the relationship between these things? And then we built this. This was with our first robot. You know, a very simple process. The machine, you know, picks a long flat, gives, you know, orients it, gives it the length, and then the human cuts, and the second human, once it's in place, screws it in place. You know, so actually it's an identical process as with the timber, but with one additional degree of freedom, the length. And what this produces is extremely interesting. You know, this is the stacking. And these were these first results. You know, it's in the same format as the previously shown brick wall. It's prototypes. It's 3 meter by 2. And here you see, you know, 3 different variations. You know, where with one mass-produced timber element, always the same section, with one process, so one cut, and the computational design process, plus the very simple pick and place process performed by the industrial robot emerge. The close up. This is interesting because this is the backside of the same, you know, completely different, you know. Although, I mean, if you look, actually you see, you know, you sense what's happening on the other side, but it's extremely minimal. This is the second one, slightly more complex, also very beautiful. You know. It's just additions of discrete elements. This is again is the backside of this same element. Okay, so these were small scale student experiments. There was no you know, discussion, yes, but, you know, structural performance and costs and all these things were not a topic. It was really about discovering something. And then a few years later, we got the chance, and this is then where Anya comes into the play. She came from Foster and Partner, came to us to the professorship, and started working on this project I'm going to show now, the sequential roof, which is 5 years ago, we got a new building, a new lab for the institute. And for some very interesting, you know, coincidence, back then the board of ETH was extremely open to experiments. And we proposed them to integrate research into the building. So if you were building anyway, you know, it would be a good chance to test something. And we said, let's scale up this timber structure. And we came up, this is the final project, with this. This is a timber roof structure. It's more than 2,000 square meters. It's trusses that have a span of 15 meters. Here you see probably the only drawing or plan that exists of this timber structure, because this was all numeric. You see then later on, because this is 50,000 small timber elements. So talking about the cross section of 5 by 10 and the length of 120 to 2 meters nailed together. And if you look at this image, you recognize how at this scale and this resolution, you know, how soft it gets. This is feels and is a fabric, textile. Of course, when it's built, it's not a textile anymore, then it's very structural, but as long as you design with it, it's malleable, because every piece is potentially and actually different, or doesn't have any reason to be identical to the last one. And this allows you, for example, you see this irregularity. These are smoke ducts, you know, from the staircases that have to go through, and everybody that already built knows that these things, you know, change all the time, and actually they get, you know, the final dimensional numbers you get often too late, you know, and then you have just to cut through your structure, what is ugly. With this design principle, we were able just to, you know, tell the fabric to make place for these ducts there. And until, because it's all parametric, until the day when production started, we were able to change this. Okay, this is the constructive systems. So it's trusses, I said 15 meters with then diagonals in them. It's produced in layers of heights of 120. They are, of course, all different, you know, because there is complete freedom of shape. And the interesting thing here is to deform this roof. Doesn't cost anything. So normally you have, you know, a very, let's say, rigid correlation between form and costs. As long as things are planar or simple, then it's cheap. And if you leave the planarity, then it's not just a bit more expensive, but it's 3 times the price. This is the logic of things as we know them. You know, with such a process, it doesn't make any difference. This roof could have any shape, you know, it would cost exactly the same and need almost the same amount of material, because it's all information making the difference. Yeah. The shape here in this roof, of course, was generated by, you know, the water flow. The water evacuation is in the columns of the building. We'll see later on. So we needed 12 low points where water would flow and would be collected and evacuated. And so this very simple design driver was, you know, informing this free form that, of course, in the interior then structures the space, you know, brings in a rhythm and so on, and plays with the light. Here you see, this is the prefabrication paradigm. If you do this in a shop, then you can install all the subsystems already. This is particularly important if you have a complex and custom form, because to introduce sprinkler pipes in here on a later stage would be a nightmare. Here it's extremely simple because it's open. And what you see here is the design, or let's say a superimposition of different design models, where the bottom right of it is what is interesting for us, because this is the designer's first decision about the logic of the roof. So you have to ask yourself, if you want to control the mutual relationship 15,000 parts, you need to decide how to control them. So what are the parameters that you wanted to be able to modify while designing? So what is your tool? And you want to be ideally free to manipulate this, in this case, these lines, these sectional lines, until the very last moment. And everything else has to propagate, because the next stage that you see going up towards the left top, this is the structural model. It's an Erstab model. that is extremely important, because in such a design, the structural engineer has to be included in the loop. And everything has to be automated, because there is no structural engineer that wants to model 50,000 different parts in order to understand what the forces are. And even if you would find such a crazy engineer, you would have just one iteration. And this is often the problem of design of complex structures, that you need a completely circular workflow if you wanted to be able to really design. Really design means to do something, evaluate against many parameters and criteria, also aesthetic ones, and then say, I don't like it, let's change it. And this change should not cause a gigantic amount of works. And then going more up to the left, you see more and more elements. And at the very end, we have what we generally understand as a BIM model, a model where everything is in. But the interesting thing here is that although it looks like a BIM model at the upper left corner, it's not a BIM model, because a BIM model normally is static. This BIM model is dynamic, because if I change the shape of one of these control lines, the BIM model adapts to it, or tells me, listen, this is not possible. I get into this conflict. Now we go to the machining part. This is what you have seen before, just bigger, but it's extremely simple. So you have an aggregate to shoot nails. This is industry standards. You have quality control. I'll show this later. This is the detail. And here you have, so what you have seen before, you have the connection. And the connection in general, but in timber architecture, is extremely important, because the connection is the weak point. Normally, structures get dimensioned against the connection and not the members. This is also why, there is a lot of engineering done in super sophisticated, timber plates, connectors, and stuff like this that introduce steel. So we'll talk about this later. Our wish here was to be extremely simple. And we identified the nail as being this connection system that is super flexible, because I can scale it. I can say I have just one nail, two nails, I have 15 nails if I really need, to transfer loads. And with the digital tool, with the robot, I can shoot them wherever I wish. Now, this possibility is at the same time a challenge, because being all these angles different and all these overlapping areas also differently shaped, and being all the connections differently loaded, this is the result then of the FEM analysis that tells you, but this one is easy, you put 3 nails and it's perfect, and the other one you need 15, and then you discover that you don't have actually the opportunity, the space to put 15, because here you see just timber code that tells you that you need a certain spacing between the nails, spacing between the nails and the edge of the overlapping area. Very simple, empirically, validated things that become a problem if you have almost 1 million nails. Because over 50,000 elements, you have 1 million nails. This feasibility area. This is what I said before. This can dramatically change. This is why you need now computation, again, to find a place where to put these connectors. And because you will not always find a solution, Then you need a strategy on how to react to this unfeasible situation. As you see here, you have, on the left, you have the problem on the very left. So nails that are outside the overlapping, the feasibility area, or are, And what you can do is to extend the horizontal one by, 1-2 centimeter or whatever. So you extend, you increase the feasibility area, or you can increase or change the section. Now, the first solution is the cheap one because it's just information. So you give it a bit more. The second one is more tricky and needed optimization, because of course you don't want to introduce the beauty and the elegance of the process the leanness of the process, just having one slat, 8 meter long, being cut in parts and placed. If you start to introduce two, it's already more complex. You have to have two, places where store them. If you have three, so it's a question of trade-off. How many different sizes you want? And this was a classical then optimization task, where you algorithmically go through all this trusses and try to find by try and error at the end, try to solve the problems iteratively and understand what this means. You say here iteration through the same. These were the three different height sections that were chosen, and then by doing this many times, you can find out where you have this sweet spot, where with the least amount of different cross sections, you can reach, or let's say have the best result. Because to increase the cross section also means that you get more cubic meter, that you need more cubic meters. So you're using more material. Now you could argue that with timber, this is not so dramatically important to save material as with concrete or steel, but still. And this was the final solution. So we ended up almost where we started. So it's a very small increase in material, because we found the places, or let's say the elements, where this is absolutely needed. And having this freedom of mixing different cross sections avoided what normally is in architecture for many reasons, economy, but also intellectual laziness, the simple solution, just to increase them all. You say which one is the weakest one. Let's do them all like this. This is also the reason why we use so much concrete. Design is not complex and elegant anymore. Because it's simpler to calculate, to design, but also to produce. Here, this logic is reverted, because for the production process, it doesn't make any difference if you use three different timber elements. And this diagram here nicely recaps this circular relationship, or this between the different design steps. So you have a design model, geometry. This is the architect. There we are at the level of water, evacuation, space. Then we have structural analysis. This has to be automated, and the interface has to be clear, so that there is no manual intervention needed in order to validate a new design option. Then you need the fabrication data. For example, the nails, because there are things that pop up that influence, propagate back to the model. And the last step is the data processing. There it's where the result of these analytical steps are let's say, inputted into the design model. And then you start with a new geometry or with new cross sections and wherever, and you do it again and again and again until you have found, I wouldn't talk about an ideal situation, but a good one. The best doesn't exist, but there are many good ones. And it's about finding a good one. Here again, now this optimization process on the whole roof. You see the, you know, with the small cross section, we would have had 340 cubic meters, while with the final model, we ended up with 390. And if you would have just said, okay, let's go for the worst case, then we would have had 300 and 540. And this is big differences. And the only thing is computation in between that makes it possible. Then, of course, these are all theoretical models. I mean, theoretical, just models. But at the end, you need to go and test these structures, real scale, in order to understand to validate your assumptions, your models. And this is then the final result. I think I have an audio here. Gilbert, can I ask you, did the movie play well? Because I don't know if I maybe I stopped the share. I forgot to switch on this. There is a checkbox here. Yeah. Okay, do you see the share again?
Yes, perfect.
Okay, good. What I wanted to show quickly, I forgot to include it into the presentation. I have a movie that shows the fabrication that is interesting, but for some reason I don't have it in here. Here we go. Now let's see if this plays. Does it play? Okay, here you see this process. You know, you have a big robot, takes the element, puts it on a saw, 2 cuts. The angle is free here, can be any angle. And then the robot, this is a robot that usually produces, you know, serial timber walls elements. And again, you see that basically it's nothing else than a gigantic 3D printing process, where the element gets deposited in the right place and then fixed with the nails. And then once the elements are printed or finished, you move them to the side and install them. Now it frees. Yeah, that's good. Okay. Let's go back. Here. Okay. Now these were it was a process that still relies on layering. This is also why it looks so similar to 3D printing process. Basically, it's layers, it's stacking. And it's has been industrialized. I would say it's fairly simple, doesn't need research. Now we go into a series of projects that are much more demanding from the technical point of view, and then they also ask for completely different solutions. The first one is a project called the Future Tree. This has been done for a client, a Swiss engineering company. This was the design, was an outdoor structure, shading a restaurant. And what you see here is that this is not flat anymore. It's curved. And the problem here is that as soon as you leave planarity, you run into a large, huge amount of problems you didn't have before, because this is now the same nail, or in this case, screw problem, that was already tricky in 2.5 dimensions in order to avoid collisions and find a place to put things. Here it gets completely 3-dimensional. But with computation, you can still manage to solve this. This is, a classical simulation on deflection and the analysis of how this structure, so the opening, in this topology, would influence structural stability. This is the elementation. So, in what chunks can you produce this? And the problem here, or the potential, is that, as you see in this movie, you have to produce this in the air, because there is no table anymore where you can, put it in order to stack elements. So these things are completely free in the air. The robot, as in the ask process, is bringing the element, it's placing where it should be, and then it can be connected. Now, this could be misunderstood as being exactly the same thing as we've seen before. And theoretically, it is the same thing. So it's a machine bringing something in space. The problem is that with a material that is not exact, and there is no physical material that is super precise, or the more precise, the more expensive and unsustainable materials get. But timber is alive, so it's a material that with moisture, temperature, and so on, deflects, deforms, stretches. So you have to deal with tolerances. And as long as you stack the elements on top of each other and then nail them, this integration of tolerance is fairly simple, because in the worst case, it's just the addition, of different, not so exact cross sections. Here, this imprecision propagates directly into the geometry and brings you in a situation where it just doesn't work anymore. But still, here we managed, but it has been tricky to build this very beautiful structure. But we encountered challenges by doing it robotically. And the same thing happened here in this second project, the DFAB house. This is a complex demonstrator, and I would like to focus on the upper part here, spatial timber assemblies. This is 2-story module sitting on a base story, built with timber, whereby everything is stiffened out with diagonals, so we have no panels. We have translucent facade. Here you see first step of this design is of course the elementation, for deciding if we are able to build it because of its complex geometry, as we have seen in the future tree, in the air, so in three-dimensional space, and not on a flat bed and then erected. Then we need to decide what chunks to produce, what logical elements belong together, and then how could we at the end connect all these parts. And out of this, you have to start to design a topology, so the connections, what belongs to what and what is connected to what. And these two things are of course interrelated. And out of this, you can then generate geometry. And as soon as you have geometry, then all this question about that we have seen before, how do things connect to each other, and then how do you build them, and where do you expect tolerances to happen or imprecision to happen, comes into play. This was now not done, not with the industry partner, but directly in our lab. And I have a movie here that shows this design process. You see here, robots bring the elements, the human connects them. Basically, it's sort of a machine act as a guide, but it's not fully automated process. So these things have been produced, trucked to the building site, and erected. You see here, everything is fitting together. So once you have assembled these things, then you have a perfect control on geometry. It's the assembly itself that is the tricky part. Very complex then. But I skipped this because I'm a bit running out of time. These interior images. Here we go. What I would like now at the end to address is this DFAB house, is demonstrating that we can build complex three-dimensional free-form aggregations of timber elements robotically. At the same time, we realized while doing this that at many ends we run into extremely complex issues and problems. Just because things were not fitting, and we had collisions and so on. All this thing can be, of course, solved. It's not impossible, and we demonstrated it, to do these sort of things. The question is it meaningful to envision full automation only because it's technically possible. You know, we have been onto the moon 50 years ago with incredibly old-fashioned technology, but it works. You know, but it has been incredibly expensive. You know. Now, since we recognized these limits, and now I want to go back to this human-machine relationship I set up at the very beginning, we realize that the best and most sustainable way to go for the future of construction is to directly integrate humans and machine into the workflow. Human and machines, I mean human, robots, but also other tools. And as long as everything is connected, so everybody, every player can connect to all the others, then this process can be extremely productive and performant. I would like to show a small video. This is a PhD work of a student of us that is almost done. His thesis is building up on the limitation we encountered in this first, let's say, robotically fabricated three-dimensional structure. And what he proposes is very interesting. It's a clamp, and the clamp is a thing that a craftsman uses. So it's a helper, a little helper that helps the robot to build structures that are, in this particular case, timber-only connections. So lap joints that are even more complex than what you have seen before, where at the end you had a butt joint and a screw. He looks into, is it possible to do complex traditional, so to revisit this possibility, because we can machine them, but also to assemble them. I just played the video. I think there is also a voice of him explaining.
The Spatial Timber Structures project investigates timber frame structures with bespoke integral timber joints. The first innovation lies in the extension of the plastic theory to timber, which in this project is adopted in the analysis and design of timber-to-timber joineries. By means of simple considerations, it allows capturing the behavior of intricate geometrical details, fostering the use of bespoke and optimized connections. In this regard, it is necessary to assess the yield condition and the plastic material behavior of timber. They are defined by a theoretical model supported by mechanical tests. The definition of the yield conditions allows identifying the structural capacity of timber and its failure modes, thus determining the governing failure mechanism for any stress states. The second innovation is a robotic assembly method based on distributed robotic clamps specifically designed to overcome the challenges of timber joint assembly. The new method uses remote-controlled and synchronizable robotic clamps in cooperation with industrial robotic arms. The clamps contain a high-force actuator to overcome friction and correct misalignment during the joint engagement. Until now, we have iterated 3 clamp designs with increasing degree of flexibility for lap joints with different angles. For demonstration, we have designed a structure that consists of 40 elements. Once a sketch is created based on an architectural intent, the design is supported by a computational tool, which interactively and in real time provides quick feedback concerning forces and assembly. After the initial phase, the process splits into 2 tracks. The first track focuses on the analysis and design of the timber-to-timber half-lap joint. Based on the global structural analysis, the forces acting on the connections are determined. The connections are then geometrically optimized in order to enable a better utilization of the joint. A software supports the intention of the designer in this process. The second track is to specify how the robotic process is performed. This includes assembly sequence, joint directions, the locations of the robotic clamps, and how the robot arm grasps each element. We formulated them as automatic design checks and provided the designer with feedback while making decisions for these interconnected problems. Once the design stage is completed, an industrial CNC timber joinery machine is used for cutting all the joints. The design data is processed to create robotic trajectories and control code for the various movements used in the assembly. This includes movements for the robotic arm to attach and detach clamps on the structure, to pick up and transfer timber elements, and for the clamps and robotic arm to move synchronously for joint engagement. In short, these are the combined efforts of the two PhD projects investigating timber joint design and robotic assembly, providing the ability to assemble structural connections in 3D, resulting in timber structures that have rich architectural and structural expressions. Thank you.
Okay. And now on this title, I would like to stop. This is the outlook. This is then our next step. We identified augmented reality as being the technology that is starting to be mature for industrial adoption, that allows to truly integrate the human into these such production processes that we have seen here. Because with augmented reality, let's go to this one, with augmented reality, the human is able to see and thus understand what the machine, what the data feeding the machine is in real time. And by doing so, the human can help the machine, be helped by the machine, or intervene. Because there are many things that are fairly and extremely simple if you do them manually, and extremely complex for a machine, and vice versa. I think if we start to now leverage on such technologies and really mix, these two reality, then this separation of jobs, equal jobs that I've introduced at the very beginning with this robot building the brick wall that we discovered 15 years ago, where the human designs, the machine executes, now can be mixed at a completely different and more interesting, an even more interesting level, where the machine can help designing, and at the same time the human can help building. And we think it's not just for sake of construction, performance, productivity, and so on, but also for socio-economical reason. It's extremely important that we leave this belief in full automation behind us, because probably it's still a legacy of 21st century, and start to conceive very complex, holistic, setups and processes where humans are as needed as machines are. And if we are able to do these transitions, then we will soon have very well qualified and retributed jobs in the building industry, that bring together the tradition of the craftsman, with the let's say education of the computer scientists, and if you're able to do so, then the fear of the end of labor probably will, not continue to dominate the discussion. But it's about, for us architects to think in these categories, because if we don't do it, if we not ask for complexity, then probably there will be other players that will just automate things, making them very simple, so adapting them to what machine can do fully automatically, and then we will run into all the problems, poor architecture and the end of labor at the same time. Thank you very much.
Thank you very much, Fabio. Amazed. Thank you. I hope you have still a few minutes to go for questions and answers. Pierre.
Yes, Fabio, great lecture. Thank you very much. The first questions that came up already during the lecture, you kind of answered in the last phase, already tapped into that. That is the role of the architect and the role of the worker. So you're already saying that is a delicate balance. How?
Yeah. It is a delicate balance, but I think the only way out of this is if we recognize that architecture design is construction, and that this separation between design and construction is indeed an artificial, invention of Renaissance. There is no deeper reason for it, and that many things we have gotten used to understand as being, just given, are, the product of certain modes of production we don't live in anymore. If you think in, dichotomy between human and machines, then we still live in 20th century or 19th century, and there I see the potential and the chance for designer, to rethink radically how things are done, at all levels.
What do you think the role of education can play in this? There's a question of an attendee who's asking, why is this not taught in architectural schools? Why do we have to find this out ourselves?
Because probably architectural schools, this stuff is fairly new, and it always needs, time is the only problem we have now, is that there is a gigantic urgency with the climate change. But other than that, we live in a super accelerated world. Things that happened in the last 40 years, 20 years normally happened in 500 years, and I don't know, even we talk about digital materiality, we don't really know what it is. You think of the end of 19th century when steel was introduced, concrete, it took 50 years until architecture, both our schools have even recognized that this has a potential. And even the first engineers, if you look at works by Maillard, I had the chance to work on a building, in a very early building, retrofitted in 1908. He did a wonderful, concrete structure and roof, but it looks like a timber structure. Took another 20, 30 years for these kind of engineers, to reinvent or to understand what it was all about, and then to bring it back into the education.
And
at the same time, it's a big opportunity for architects, to just do things,
And how is it, for instance, this method of design and processing, how is this compatible with existing buildings? What are the chances for parametric design in relation to redevelopment of existing buildings?
In the redevelopment, I think this is not a problem, because we have, the data acquisition is gotten extremely simple. With a very cheap scanner, you can scan a building down to the millimeter, and you know exactly what is there. And once you have what is there, you can also plan the addition. I don't see a problem. I would say the biggest limitation to the broad introduction of parametric design is education, probably, because as long as there are not enough people in industry and in design and engineering that are at home with this thinking, then this thing cannot happen large scale, but it's a matter of year. I think that the next generation of architects, so the people who are studying now, grow up with these things. So when I studied, I drew my diploma in 96, by hand with a pencil.
Yeah, same here.
This is not crazy. This is 30 years ago.
Yeah.
26 years ago. So it's yesterday.
Yeah, it's incredibly fast.
Yeah.
Thanks a lot, Fabio. I think maybe we can conclude this session now, because maybe people would like a short break before we continue. What do you think, Gilbert?
I'm very sorry. I have a PhD defense that I have to chair.
Yeah, I know. You have to go somewhere else. So.
I'd like to stay with you and follow the final discussion. But thank you very much. And I hope you will have a a nice afternoon.
Thank you
Well,
very much. And I hope I see you back soon.
Yeah, we will stay in contact.
Yes.
Bye-bye.
Okay.
Bye.
Bye-bye,
Fabio.
Fabio.
Bye, everybody.
Yes, we have a short break. I provide for 15 minutes. And then at 15:20, maybe let's stick together 15:15, and then we go further. Thank you.